Hello everyone, it's Dr. C. What I wanted to do in this video was record one example problem of a limiting reagent problem. So let's just do this very quickly. Let's look through this problem and see what we need. So let's just read through this together. A fuel mixture used in the early days of rocketry is composed of two liquids. That's interesting, but that's not relevant to how we're going to solve this problem. Hydrazine, N2H4, and dinitrogen tetroxide, which ignites on contact. So what you should pull out of that is that N2H4, hydrazine, and N2O4, dinitrogen tetroxide, are our reactants. Let's see what we produce. They ignite on contact to form nitrogen gas. Now, nitrogen gas, is it just nitrogen atoms? Think about a lot of the gases like oxygen and hydrogen and fluorine. Yeah, those are diatomic. Okay, so nitrogen gas. We don't have to put the phases in, but we could. And water vapor. Okay. Now, these are liquids if we want to put in the phase. It says so in the problem. All right, so there's our reaction. Now we're going to do some stoichiometry. What do we need with that balanced equation? Yeah, we need it to be balanced. We need that equation to be balanced. So let's do that. Now, typically with reactions that have hydrogen and oxygen, we're going to balance everything else first. So we would typically start this problem and we would say, okay, we have 2 plus 2. We have 4 nitrogens. So I'm going to need a 2 there. And then we come over to the hydrogen. There's 4, so we put a 2 there. Boy, something's wrong, isn't it? Because now I have 4 oxygens, but I only have 2 over on the right. That's a problem. So in this case, it didn't work starting with everything other than hydrogen and oxygen first. In this case, we see there's 4 oxygens. Well, the only way to get 4 oxygens is now to put a 4 in front of the water. Okay. Now that's going to give us 8 hydrogens. So I'm going to have to put a 2 over here. And now 2 times 2 is 4 plus 2 is 6 nitrogens. So now I'm going to need a 3 there. Is that balanced? I think so. 6 nitrogens on each side, 8 hydrogens on each side, and 4 oxygens. Remember, hugely important to have a balanced equation because stoichiometry is all about mole ratio. And you have to have the correct mole ratio between reactants and products. All right, balanced equation, we have that. Now let's continue with this problem. How many grams of nitrogen gas, so we're looking at producing nitrogen gas here, form when 100 grams of N2H4 and 200 grams of N2O4 are mixed? All right, what kind of stoichiometry problem is this? And I gave it away with the title. But you should be thinking about this. Recognizing problems is really key. You should recognize this straight away as a limiting reagent problem. We have the amounts of both reactants. Most likely one of those is going to run out first. We need to figure out which one. So the method that I like is we're going to treat each reactant separately. Now you will notice I put a decimal point after 100. Technically we should write this in scientific notation, but let's assume we have 3 sig figs with that number. We're going to do a second calculation with the other reactant. So what we're going to assume here is that in the first calculation, all of the N2H4 reacts. If it all reacts, how much product are we going to get? We're then going to do the same thing for the second reactant. If all 200 grams of N2O4 react, how much product can we get? And then we're going to compare those two amounts of product. All right, so we want to go from reactant to product. How do we compare things in a balanced equation? How do we compare them? Yeah, we compare them in terms of moles. So your first thought here should be, we have to get to moles of N2H4. How do we do that? Yeah, we use the molar mass. So calculate the molar mass of N2H4. 1 mole of N2H4. Each nitrogen is a little more than 14, about 1 for each hydrogen. You should get about 32, and I calculated 32.05 grams per 1 mole. Okay. Watch your units so that in this case, as we see grams cancel, now we have moles of N2H4. Now we can get the moles of anything in that balanced equation using the mole ratio. Right? We want to go to moles of nitrogen because the problem says how many grams of nitrogen gas form. So we don't want to go to water vapor because that's not what the problem is asking. We're going to nitrogen. So let's use that mole ratio. 3 moles of nitrogen. We just use the coefficient in front of N2 per 1 mole, oh, not 1 mole, sorry, 2 moles of N2H4. Coefficient of 2 in front of N2H4. Again, unit conversion, make sure that the appropriate unit cancels, giving you the unit that you want. In this case, moles of nitrogen. And if you calculate this out, and hopefully I did it correctly, I came up with 4.68 moles of N2. All right. So that's one reactant. We're not done with this problem because we still have to do the other calculation and see which reactant limits how much product we can get. So let's do the same calculation for N2O4. Again, we need moles so that we can get to moles of something else using the mole ratio. Calculating the molar mass of N2O4, 2 nitrogens at about 14 each, 4 oxygens at 16 each. I came up with 92.02 grams of N2O4. Again, arranged properly so that grams cancel. Now we have moles of N2O4. We can then apply the mole ratio now to get the moles of anything else in that equation. Of course, we want to go to moles of nitrogen, coefficient of 3 in front of N2. What's the coefficient in front of N2O4? Yeah, it's a 1. So we don't write the 1s in there, it's understood. Again, arranged properly, so moles of N2O4 cancel, leaving us moles of nitrogen. And I calculated 6.52 moles of nitrogen. So we have 2 answers for the amount of product. Which one is right? Which one limits how much product we can get? Which reactant limits how much product we can get? And we see that the smaller answer is correct. We will never get to that larger amount because the N2H4 has run out. N2H4 has run out. Therefore, it is our limiting reagent. Okay? So N2H4 runs out, reaction stops at 4.68 moles of product. We would then say that N2O4 is in excess. That's our excess reactant. All right, now you will notice that I stopped at moles. What does the problem ask for? How many grams? Now when I work these, I like to stop at moles because I know this second calculation in this case is not correct. So why should I continue an extra step if I don't have to? Now, to get to grams, I simply have to take the correct number of moles. And how do we go from moles to grams? Yeah, we need the molar mass. Molar mass of nitrogen is going to be a little over 28. It's about 28.02 grams of nitrogen in 1 mole of nitrogen. Moles cancel, leaving us grams, which is what we want. And we end up to 3 sig figs, about 131 grams of nitrogen. And there's our correct answer. All right? There you go. That's a limiting reagent example problem. If you're comfortable with that, great. This problem did not ask you to calculate the amount of excess reactant left over. We know N2O4 will be in excess. Let's go ahead and do that just for practice. All right, let's try to figure out how much N2O4 remains. All right, so we answered the question that was there. How much nitrogen gas is formed in terms of mass? We're done. But what if the problem then went on to say how much excess remains? So let's write another problem here. I'm going to switch color to differentiate these two. Scroll down a little bit more here if I can. Sorry, I wrote a little sloppy there. So how many grams of excess reactant remain after reaction? After reaction. All right, so the first thing you have to identify is your excess reactant. We know N2H4 was limiting, therefore N2O4 must be in excess. So how are we going to work this? Well, there are a couple of ways to do this problem, maybe more than a couple of ways. The way that I like to work this, since we stopped at moles of each of these, is to subtract the smaller number of moles from the larger number of moles. And we'll talk about why in just a second. Okay, and when I subtract those, I get 1.84 moles of N2. Well, what is that? Because that just seems like some random thing. Okay, we got two answers. We know the 6.52 is not right. Then I just subtract them and I get a number. Well, the way I like to think of this is the extra N2 we could have produced if all of the N2O4 had reacted. Okay? We're never going to get that extra N2 because N2H4, the limiting reagent, ran out, reaction stops. But let's, in some magical world, the N2O4 kept reacting somehow. How much more N2 could we get? That's how much more we could get, 1.84 moles. We're then going to take that amount and work backwards to see how much N2O4 is in excess. And how are we going to go from N2 to N2O4? Yeah, we use the mole ratio from the problem. So we have 1.84 moles of N2. I've scrolled off the screen here, but hopefully, well, I guess we should scroll back up. What's our mole ratio? We have a 1 in front of N2O4 and a 3 in front of N2. Moles of N2 cancel. Now, I asked for how many grams of excess reactant remain. This would give us moles of excess here. How do we go from moles to grams? Yeah, we need the molar mass. And the molar mass, as we calculated above, is 92.02 grams of N2O4 in 1 mole of N2O4. All right, moles cancel. And we should get and this would be in excess. 56.4 grams of N2O4 in excess. All right, not too bad. Guess I should have separated these two problems. So, quick check. This is the quick check. So say you're taking an exam, you don't have any extra time. The quick check would be to say, well, does that answer at least make some sense? Well, yeah, it does. We started with 200 grams of N2O4. Some of it reacts, so we're going to have less than 200 grams left. We have 56.4 grams in excess left over. All right. Now, say you're taking an exam and you have more time. You've cranked through the exam, you've done great. You want to go back and just double check your work. How could we check to make sure that that was really correct? And one way to do that would be to take our 200 grams. Remember, we started with 200 grams of N2O4. we know we're left with 56.4 grams, or at least that's what we calculated. I'm sorry, I left my N2O4 off here. And so what we end up with there is 143.6 grams of N2O4 reacted. Okay, you with me? So we started with 200 grams of N2O4. We just calculated that we have 56.4 grams left over. That must mean that 143.6 grams reacted. Well, if that 143.6 grams reacted, how much N2 could we get? Remember, from our limiting reagent, we got 4.68 moles. We should get the same number from the amount of N2O4 that actually reacted, if this is indeed the right amount, 143.6. Okay, so like I said, on an exam, when you're pressed for time, I wouldn't do this unless you get to the end and you still have time left. So let's do a little more stoichiometry. Stoichiometry is fun, right? Okay, we need moles, right? So we can go to moles of something else. 1 mole of N2O4, 92.02 grams. Again, we have the molar masses and the mole ratio, so you don't have to recalculate these. So that will make it not too bad. And it was 3 moles of N2 for 1 mole of N2O4. Look back at your work. Look back at the equation. And guess what we come up with? 4.68 moles of N2 produced. Check. Right? We solved it correctly because that amount matches the amount we got from our limiting reagent. And that should not surprise you. If this is the actual amount reacted, 143.6, that should all run out and produce the same amount of product. So the amount of excess, we must have been right, 56.4 grams. All right, so we did check and double check. It's kind of like the discount double check. Oh, that was really bad. Never mind. Forget I even said that. Okay, I hope this helps, and have a great day. Take care.